morning, Steve. This is Bob Nicholson with the Calgary Eye Opener. Have a good day. And by the way, if you're overhead, can you tell us what traffic's like on the boat trail headed into downtown? Hey, but don't worry about it. Even if you can't, we hope you have a wonderful day with the best view in the whole world of the sun coming up over Alberta.
Good morning. Get up.
Joking. Mr. McLean, I'm proud that you're Canadian, and I'd just like to say that we're all behind you 100%. If there's any other life out there, bring them back.
Watch out for Darth Vader.
Good morning. Happy Monday if it's a Monday. Happy Tuesday if it's a Tuesday, and so on.
This is Bill down here on Earth. Martians. I'm interested in Martians. If you just get me an autograph.
Good morning, Mr. McLean. Wishing you all the best.
Do what you have to do up in space and then come back and have a party.
We have a beautiful fall, and come back soon and see us.
Oh, and Steve, before we let you go off and have your first cup of freeze-dried coffee, we just wanted to let you know that the music you're hearing is a morning prayer song of the Blackfoot Indians of southern Alberta. It's meant to show respect to the Creator so that He'll watch over you in your daily endeavors. You know, the Blackfoot say this song will prepare you for the days to come.
Good morning, Columbia, and by the way, there are celebrations in the street of Toronto.
Good morning, Houston. Thanks for the music on the New Frontier.
We copy and understand Steve's going to collect on a few bets today.
All right.
And we're on the flight deck, Mike.
Okay, great. Steve working on steam.
Canadian payload specialist Steve McLean on the aft flight deck of Columbia is working with the Sun Photospectrometer Earth Atmosphere Measurement Experiment. The SPEAM is a handheld instrument which McLean uses out of the window of Columbia to look at the Earth's upper atmosphere. It's a spectrometer which can make measurements of the ozone and nitrogen compounds, which play an important role in controlling the ozone balance, especially in the presence of chlorine in the upper atmosphere. Also, this is a look at the heat pipe performance experiment, which is underway on the mid-deck. It's a spin test for the heat pipe technology, which is being tested aboard. Heat pipe technology is a method of cooling that could be used for future spacecraft, which uses no moving parts. This spin test of the heat pipe is designed to mimic the type of accelerations and disturbances it might experience on a spacecraft, and see how well it performs.
Go ahead, Columbia, and we've got a good picture from the flight deck.
Okay, thank you very much. Commander Jim Weatherby again. This time I have Dr. overhead in Columbia. I'd like to give you a mission status summary of what's been going on today. It's been a pretty interesting day and very hectic. We have a lot of different people doing a lot of different things, and we'll talk a little bit about them right now. One of the experiments is the heat pipe performance experiment, and I'll turn it over to Tammy briefly.
Good morning. The heat pipe performance
experiment comes out of Hughes Aircraft, and it has some very practical applications to the design of heat pipe systems which are used on commercial satellites. Heat pipes, quite simply, take heat and transport them from one place to another. For instance, on a communication satellite, from a hot electronics package out into space. There's not a great deal of data on the microgravity performance of heat pipes. And so during our mission, we're going to get some sort of idea of how well heat pipes perform in microgravity, meaning how well they transport heat. And we ran a series of tests this morning investigating the productivity of heat pipes. Some of the tests, the heat pipes were static, and for some of the other tests, the heat pipes were spinning, because as you know, some of these satellites in orbit are spin stabilized. And back to you, Jim.
Some of the other things that have been going on in the middeck, I was working on all at the very same time, I was working on a protein crystal growth experiment, trying to put some food into the galley with one hand holding a light for Biggs, who was taking photographs of a EDO extended duration orbiter new fan separator that Lacey was taking pictures of, while Biggs was filming the new fan separator test. He was holding one of Tammy's legs down so that she could work on the heat pipe experiment, and Chep is overhead. We're going to take you down to the middeck now and show you the layout. Chep works on the ceiling on a crystal vapor transport experiment, and I'll now give you some downlink TV on the middeck, and we'll slow down and talk about some of the things going on down below. We probably don't have a whole lot of time left. I will say that if Shep needs to ask anything off the ground, we'll turn it back over to him to get any information that he needs for his experiment. It's a pretty expensive experiment that he's endeavoring to set up right now. It's an experiment by Boeing, growing crystals by vapor transport. Okay, behind Shep you can see is the MAR, or middeck accommodations rack, and it is the place where we have two furnaces that will be growing the crystals over the next several days. It's of course, a microgravity flight, and so we really need to be careful and not bang around and knock into the lockers as we grow these very expensive crystals. Bakes is going to float around and show you the setup for the heat pipe performance experiment that Tammy talked about. We have 4 of the heat pipes installed inside of the experiment. And it has various thermistors around the heat pipes for measuring the temperature and the ability of the heat pipe to dissipate the heat. Okay, lastly, we'll pan around and show Steve over in the dark corner by the hatch, and he's performing an O-glow experiment. They're measuring the glow of the Earth as it flies through the solar system. The oxygen molecules, or atoms in the upper atmosphere, get excited from the movement of the Earth through the solar system, and with the camera apparatus, they can look out the window and measure the amount of glow, and it has applications in measuring the effects of the ozone layer in the upper atmosphere. And it's probably pretty dark over there in the corner. They need to have that side of the orbiter dark in order to take the pictures, and so we won't be able to turn any lights on to show you what's going on out there. Thank you very much for today, and I guess we'll try to get back to you in the future.
Thanks, Wex. That was good. We got a good copy on everything, and we had TV for the whole show.
Okay, thanks. Great.
And I got some words for you on CPCG.
This is Space Lab Mission Operations Control in Huntsville. while the crew of Columbia goes about their activities today. On this fourth flight day of the mission, the U.S. microgravity payload array of experiment systems in the cargo bay of Columbia is continuing to operate smoothly without any need for crew attention. The USMP-1 experiment systems have been keeping scientists and engineers here in Huntsville busy, however, as the data they've been looking at, they've been working so long to acquire, is now actually being produced by the experiments and being received here on the ground. Scientists for the 3 investigations that are being performed on this first flight of the U.S. microgravity payload say they're very pleased with how operations of their experiments is proceeding. Those 3 experiment systems are the Lambda Point experiment, which is an investigation in fundamental physics, and the Mephisto furnace, which is studying detailed processes of solidification of metallic alloys under microgravity conditions, and the Space Acceleration Measurement System, which is gathering acceleration data to characterize the low-gravity environment provided by the Space Lab platforms on which the experiments are mounted. The Lambda Point experiment team reports that their experiment is operating well, and it has now begun collecting high-resolution data on a sample of ultra-cold superfluid helium using thermometers that are accurate to within billionths of a degree. We're currently taking a look in their working area. The principal investigator for the Lambda Point experiment, Dr. John Lipa of Stanford University, here in the left-hand portion of our current view on NASA Select. These current operations follow the completion yesterday of a very precise calibration process to make sure the experiment's high-resolution thermometers and the helium heating system are working as they should. Having completed those preparations, the team established that the instrument should be able to test Dr. Kenneth.
We're approximately 2 minutes from LOS. We're going to pick you back up on the other side at 2331. Just a couple of notes. Due to the USMP run, we've had a request to push the IMU align back to 3 days, 0 hours, 40 minutes to begin the maneuver, and also
break, Sam. You were broken, and I didn't hear what you said. Start over, please.
Okay, Jim. What we're going to do is we're going to push the IMU align back to 3 days, 0 hours, 40 minutes for the maneuver due to the USMP run. And we'll also delay the waste dump. We'll get to you on the other side at 2331 with details.
Okay, great. I was just getting ready to do that, so thanks. We'll delay the 40.
And Columbia is now out of range of the tracking data relay satellite system and will be for approximately 6.5 minutes. Again, in terms of the activities of the Lambda Point experiment team, since they've now completed their preparations, their very precise calibration procedures, they have established that the instrument should indeed be able to test Dr. Kenneth Wilson's renormalization group theory with far greater precision than has been possible on Earth. That so-called renormalization group theory provides a mathematical explanation for the dynamics of matter near critical transition points. These transitions, phase transitions as they're called, such as that between liquid and gas state of matter, are common phenomena in nature and technology. Scientists are particularly interested in what they term cooperative phase transitions, where all the regions of a fluid behave in the same way at the same time. For instance, at the lambda point of liquid helium, the helium changes from a normal fluid to a superfluid, becoming a virtually infinite conductor of heat and flowing without friction. During the experiment runs of the Lambda Point experiment, such as are currently underway, tiny heat pulses are used to carefully raise the temperature of a small sample of liquid helium take it through the extremely narrow temperature range where it begins to go into the transition from superfluid to a normal liquid state. And we're currently looking at some of the telemetry data that shows temperature conditions as the Lambda Point team has been conducting that experiment. The temperature differences which we're seeing here as the sample of liquid helium was very gradually being heated, these temperature increments are in the range of billionths of a degree Celsius. So the degree of control over this experiment to conduct it properly and measure the data is far beyond the limits of sensitivity of any other type of experiment. And this can only be done by getting to this level of accuracy, by getting out of the disturbance and the masking effects of Earth's gravity. The Lambda Point, again, occurs at approximately 2.17 degrees above absolute zero, and the bottom line key data that's collected during this experiment is not actually the temperature at which that phenomenon occurs, but the heat capacity of the liquid helium, which is the amount of heat input that's required to raise the temperature of the substance by a specified amount. Another feature that's come out of this experiment so far is the data analysis by the team. Here indicates that the instrument is less sensitive to radiation disturbances in the area known as the South Atlantic anomaly, and also less sensitive to orbiter motions than they had expected. So this should allow the team to continue collecting data during some periods when they previously had thought it might not be possible. In one of the other major experiments on this USMP payload, the Mephisto experiment, the tests of a alloy of tin and bismuth using a sample in the Mephisto directional solidification furnace have revealed that its quality is very uniform along a 6-inch section of the sample. That's the portion of the samples that are actually being melted and resolidified during the repetitive experiment runs. Within that 6-inch portion, the experiment team is decided to do all of their melting and solidification runs along a particular 2-inch section of the samples in order to eliminate some of the experimental variables. This Mephisto experiment is different from crystal melting and solidification furnaces that have been flown on previous Space Lab and shuttle missions, in that it allows the controllers, the scientists, to actually visualize the crystal solidification as it's happening in space. And so far the Mephisto science team, headed by Dr. Jean-Jacques Favier, Dr. Favier visible here in the center portion of our screen, looking at some of his data, standing up at his console. Dr. Favier and other members of his team say that they've so far observed some phenomena that are completely different in space than those observed in comparable ground-based experiments. They've also noted that the Mephisto furnace runs just a little bit faster than expected in terms of its movable furnace traversing along the sample, so that has provided them time to repeat some of their experiment stages overnight. So in general, the 3 experiment systems of the U.S. microgravity payload continue to function very well, with the only item involving any unplanned attention being an occasional need to reset a power relay that supplies one of the 2 Space Acceleration Measurement System units. That unit experiences occasional data dropouts, but by recycling the power relay, it resolves the problem, and those interruptions have not caused any loss of essential science data. So for the next several days, these 3 US MP1 instruments will continue to take data. As with all science investigations, multiple data takes are very valuable for establishing a reliable database. So at 2 days, 23 hours, 30 minutes mission elapsed time. That's an update regarding the U.S. microgravity payload activities in this STS, STS-52 flight.
Okay, Sam, you ought to be getting it now.
That's affirmative, Bakes. We're getting it.
This is Mission Control. This is a downlink from the middeck of Columbia of the crystal vapor transport experiment. This experiment grows crystals by heating solid materials to a vapor, then letting the vapor cool and crystallize. Experimenters hope to grow semiconductor crystals bigger than we're able to grow on Earth.
And Columbia, Houston, they are seeing the spectacles that you had referenced, and they're evaluating.
Okay, Sam, we're going to try and rig the fiber scope, give you a little better view, but they're fairly pronounced.
I think we have three runs from this view, and then 2 or 3 runs viewing some of the other parts of the system.
Okay, Lacey.
This is Mission Control. This is video replay from Columbia of a test called DTO, or Detailed Test Objective number 657. It's footage that the crew has recorded of the operations of the new fan separator for the waste containment system.
This is Space Lab Mission Operations Control. Operations with the experiments on the U.S. microgravity payload in the shuttle's cargo bay are continuing on a 24-hour-a-day basis, as are the science support operations here at the Huntsville Space Lab Operations Support Center. Since activation of the experiment systems on Flight Day 1, they've been operating with very little need for crew involvement. All 3 experiments, the Lambda Point investigation, the Mephisto furnace, and the Space Acceleration Measurement System, operate on a heavily automated basis using a large inventory of programmed timelines that were written pre-mission and which are now executing. However, they also permit and sometimes require intervention from scientists and engineers on the ground, for instance, to change experimental parameters or to downlink data to the ground. And when that's done, it originates with experiment team members here in the Huntsville Science Operations area, using their ground support systems and sending the commands directly to the experiments in Columbia's cargo bay. This mode of operations is termed telescience by the scientists and engineers, and it's a precursor to the mode of activity that's likely to be quite common in the early stages of Space Station Freedom operations, in the period before it has permanent crew members on board. Currently, the Lambda Point and Mephisto experiments are well into the intensive data acquisition portions of their operations. Each of those experiments is performing multiple data runs, varying some of the parameters on subsequent runs, or in some cases conducting repetitive runs under the same conditions so as to establish that they have a reliable basis for what they're seeing. The Lambda Point experiment team is continuing to collect high-resolution data on a sample of ultra-cold superfluid helium. An incidental note regarding their terminology: when they talk about being in the high-resolution mode of operation, they are varying the temperature of their small helium sample inside the experiment system by increments measured in a few nanokelvin. 1 Kelvin is a unit of temperature equivalent to a degree Celsius, and a nanokelvin is 1/billionth that size. So their critical experiment runs in the high-resolution mode consist of raising the temperature of the liquid helium sample so it approaches the so-called lambda point, starting from about 30 or 40 billionths of a degree below the lambda point, and then going just barely above that point. This, of course, is occurring at temperatures just a couple of degrees above the absolute 0 point, the coldest possible temperature. And the key data that they're accumulating with these measurements is the heat capacity, also known as the specific heat of the liquid helium. And in physics, that refers to the amount of heat input that's required to raise the temperature of a substance by a specified amount. The lambda point is such an interesting phenomenon because right at that point, the heat capacity of liquid helium has been observed to increase radically, and this is also the point where helium undergoes the transition from its exotic superfluid state to the normal liquid condition. And by obtaining a better understanding of this transition, scientists expect to be able to better understand phenomena on as large a scale as the dynamics of a hurricane. We're currently looking in that working area where the principal investigator, Dr. John Lipa, here on the left, is discussing the experiment operations with the project scientist, the experiment scientist, Dr. Ulf Israelsson, on the right. Lipa is with Stanford University, and Dr. Israelsson is with NASA's Jet Propulsion Laboratory. Meanwhile, the Mephisto experiment, or materials for the study of interesting phenomena of solidification on Earth and in orbit, is also in a period of repetitive runs. In the case of this investigation, the key operation is a series of heating and cooling cycles in which 3 samples of an alloy of tin and bismuth are melted and resolidified. Actually, a particular portion of each of the samples is melted and solidified each time by having a movable furnace inside the Mephisto apparatus track back and forth across a 2-inch length of the samples. While this is happening, data on the subtle processes of solidification are being acquired and monitored and recorded. Those data are in the form of electronic signals, which allow the science team to visualize the subtle aspects of crystal solidification in real time as it's occurring in microgravity. The data, in other words, are acquired non-invasively without disturbing the crystal growth process itself, and that provides an insight into the temperature and concentration characteristics at the moving solid-liquid interface. This information is valuable for predicting how good the ultimate metallurgical properties of the material will be. These Mephisto measurements are made at a series of different rates of furnace movement, and they start out at a relatively fast rate of about 1/16th of an inch per minute, and then reduce that rate on each of 4 subsequent passes. Currently looking at the principal investigator for the Mephisto experiment, Dr. Jean-Jacques Favier of the French Atomic Energy Commission. In support of both of those experiments, meanwhile, the Space Acceleration Measurement System is continuing to measure and quantify specific accelerations and vibrations caused by shuttle motion. The separate SAMS units are mounted on or near both the Mephisto and Lambda Point experiments, and helping scientists for those teams to track any subtle disturbances that might affect their investigations. In connection with the SAMS measurements, during this USMP-1 phase of the STS-52 mission, there's a group of data interpreters stationed here at the Space Lab Science Operations area to define subtle orbiter motions that are picked up by the Space Acceleration Measurement System almost as they're happening. This group is known as the Acceleration Characterization Analysis Project, and they're working closely with the other U.S. microgravity payload experiment teams to identify and interpret various accelerations. The SAMS, of course, has flown several times on the shuttle, and that's part of a program designed to establish the cause and effect relationship between low-level accelerations and the microgravity science experiments. So overall, the experiment systems of the U.S. microgravity payload are continuing to perform very smoothly, and operations are staying very close to the pre-planned timeline, or in some cases actually a little ahead of the pre-planned schedule. The only item that's been involving any unplanned attention is an occasional need to reset a power relay that supplies one of those two Space Acceleration Measurement System units. We're currently at 3 days, 2 hours, 43 minutes mission elapsed time, and this is Spacelab Mission Operations Control Hunts.
This is Mission Control. These are payload bay views from Columbia's cargo bay cameras as it comes across the Pacific Ocean, approaching the western coast of Mexico. It'll sweep down over east central Mexico and down over the Gulf of Mexico, barely coming across the most northeastern tips of South America on orbit number 50. Aboard Columbia, Commander Jim Weatherby is conducting a wastewater dump. This is another phase of it. He's been doing a phase of the wastewater dump a little earlier and has started it again.